Welcome back. We're going to wrap up 9.6 on the ratio root test by looking at some additional examples of using the ratio root test, maybe some more involved examples. And before we can get to those examples, I want to note some two special limits that are going to become useful. The limits are limit as n goes to infinity of 1 plus 1 over n to the nth power, and also the limit as n goes to infinity of the nth root of n. These are two special limits that we're going to look at. Now, they're not series right now, so we're not talking about series or the ratio root test. We're just talking about these special limits, and they're going to become useful when I use the ratio and root test. And so let's look at both of these limits. Now, say we take the limit as n goes to infinity of 1 plus 1 over n to the n. And say that equals L. Now, we don't know what this limit is, but it's actually an indeterminate form. If we let n go off to infinity, this term inside of the parentheses is going to 0, and 0 plus 1 is 1. So we get 1 to the infinity power. That's 1 times itself infinitely many times, and while we may think that 1 times 1 times 1 is 1, any finite number of times that's true, but when I multiply 1 to itself infinitely many times, that is actually unknown. 1 times 1 times 1 times 1 to the infinite power, right? If we do this forever, we're not quite sure what happens. And so this is actually an indeterminate form. Unfortunately, though, this is not an indeterminate form in which I can use L'Hopital's rule on. Remember, L'Hopital's rule only works for 0 over 0 or infinity over infinity. And so I'm going to manipulate this indeterminate form to get it into a form in which I can use L'Hopital's rule, because otherwise I'm not going to be able to get an answer. And so let's say that the limit of this sequence is L, the limit of this thing. And I don't know what this limit is, but I'm going to use a very fancy trick in math, because that whole to the infinity power scares me. There is a function in math which allows you to write exponents as coefficients. That function being natural log. You're learning in algebra or in Calc 1, right? If I have a power inside of the log, so the log of something to a power, that power can be written as a coefficient. Why do I want to do that? Why would I ever choose to take ln of both sides? Is because, of course, remember, we want to transform this into an indeterminate form that I understand. Now we have a product of things, but of course, L'Hopital's rule requires a quotient of things, either 0 over 0 or infinity over infinity. And so let's go ahead and make this a quotient. We can always make a product a quotient by taking one of the terms in the product, throwing it in a denominator by taking its reciprocal, so then 1 over n. This is the same thing, right? Dividing by 1 over n, multiplying by its reciprocal would be this. So I'm just taking a product and writing it as a quotient. You can always do that. Equals ln of my answer. Now, why do I care about this? Well, let's see what happens now. When I let n go off to infinity, the numerator becomes ln of 1. Right? 1 plus 1 over n goes to 1. And ln of 1 is actually 0. If I let the denominator go to infinity, then I get 1 over infinity, which also then goes to 0. And so look, I have an indeterminate form now in which I can use L'Hopital's rule on. And so now using L'Hopital's rule, so this is the L'Hopital's rule jump now. I take the ratio of their derivatives. So we have to remember the chain rule and derivatives. Remember, the derivative of ln is 1 over whatever's inside. So 1 over 1 plus 1 over n times the derivative, right? The chain rule kicks in. I need to multiply by the derivative of 1 plus 1 over n. The derivative of 1 is 0. The derivative of 1 over n is negative 1 over n squared. Just using my power rule, right? N to the negative 1 becomes negative 1, n to the negative 2. And the derivative of the denominator, well, the derivative of 1 over n we just did a second ago, negative 1 over n squared. Which is actually great, because now that means those cancel. And this equals ln of my answer. Now that these are out of the way, now I can take this limit, right? These are gone. They've been canceled. When I take the limit as n goes to infinity, now I get 1 over 1 plus 0. So it looks like my answer on this side is 1. Now, however, the limit is not 1 though, and this is where it becomes important to understand we used ln at the beginning. 1 is not L, 1 is ln of my answer, and so if we use algebra, we can undo ln by now exponentiating both sides. And so what is L? It's e to the 1 power. Raise each side as a power of e to undo the ln. And so if 1 is ln of L, then L is e to the 1, which is just e. And so this is a very special limit. This limit is actually a definition of the very special constant e. We use L'Hopital's rule to show it. Now let's do the other one. And the reason I paired these together is because you use the same exact trick to evaluate this one. Limit as n goes to infinity of the nth root of n. Think of this as the limit as n goes to infinity of n to the 1 over n power. That's the nth root of n as well, right? Writing a root as an exponent. And again, say that this is equal to L. We don't know what L is. We'll find out. We can't evaluate this directly because, again, it's an indeterminate form. The thing right here blows up to infinity, what's under the root. The root, though, goes to 0, right, to the 0 power. So you have infinity to the 0. Now, you're told that anything to the 0 power is 1. Well, what about infinity to the 0 power? And that becomes a little bit unclear. It's indeterminate, in fact. Now, it's not an indeterminate form that I understand. It's not 0 over 0 or infinity over infinity, so I can't use L'Hopital's rule. But just like I did here, I'm going to use the same exact trick to solve this. I'll take ln of both sides. So then I'll be able to get ln of my answer. Why do I do that? Because there's a nice property of log, the only function that allows me to do this. Take an exponent and write it as a constant in front. Now, actually, I can just write this as a quotient. I don't even need to take a reciprocal. And if we take this indeterminate, or if we take this limit, the numerator ln of n blows up to infinity, the bottom blows up to infinity, we get an indeterminate form in which now we can use L'Hopital's rule on. Using L'Hopital's rule, we get the limit as n goes to infinity, 1 over n, the ratio of their derivatives, over 1. Well, that's a nice limit now to take. The 1 divided by 1 means nothing. 1 over n goes to 0. And so on the left-hand side, we get 0, and 0 is then equal to ln of my answer. And just like we did here, that's not my answer. My answer is then exponentiating both sides, would be e to the 0. Now, e to the 0 is 1. Anything to the 0 power is 1, as long as it's not infinity. E is some number. And e to the 0 is 1. And so that tells me that this limit is 1. So anytime we encounter either one of these limits or maybe a variation of one of these limits, we can remember this bit of information, these special limits. This goes to e and this goes to 1 as n goes off to infinity. Now the only thing I'll do is I'll take this guy here and I'll rewrite him. He might be useful in a second. As a single fraction with a common denominator would be this. This limit's n plus 1 over n, right? I just found a common denominator of n, then adding them together gives me n plus 1 in the numerator and in the denominator, still to the nth power. We're good. Now, if we look at these two special limits, let's go ahead and go and do some examples that may involve these two things. So we're going to do the ratio and or root test to determine the convergence or divergence of these series, and some of these things may come up to play. And so let's take this ratio. N factorial over n to the n, have a negative 1 to the n in front, so it's alternating. And in this case, because I see the factorial, I am kind of limited. I'm going to have to use the ratio test here, because I can't do the root test, and I have no other way to deal with factorials. And so I'm going to do the ratio test, so we're going to take the limit as n goes to infinity. The ratio of consecutive terms, we just have to be careful how we write it. Be careful, this is n plus 1 to the n plus 1th power. by replacing n with n plus 1. We get this. Not very nice looking, but let's simplify it and see what we can work with. Multiply by the reciprocal. The absolute value takes care of the -1 to the n's. Those just go away because of the absolute value. I don't need to worry about them anymore. And we get this. Now let's go ahead and simplify the factorials. That I can do. This factorial goes from 1 up to n. This also goes from 1 up to n, but then one more term to n plus 1, and so everything would cancel except for a single n plus 1 in the numerator. But now I also notice something that's going to happen here. This is exponentiation on n plus 1. So this is multiplying n plus 1 times itself, n plus 1 times. Well, I have an n plus 1 in the numerator, so actually that n plus 1 that was left over from the factorial can cancel with one of the n plus 1s in the denominator. And so after I simplify this, I should be able to rewrite it as absolute value doesn't matter anymore. I've already used it, taken care of it. N to the n over n plus 1 to the n. Now, just using rules of exponents, since they have the same power now, we can write this as n over n plus 1 to the n. Now, this should look somewhat familiar. In fact, we just talked about a special limit that gave us something similar to this type of limit. So if I just go back to the other board for a second, you look here and you realize that if I had n plus 1 over n to the n, I get e. The difference is over there, I have n over n plus 1 to the n, the reciprocal of it. Well, that's not bad, because now that just means I'm going to get the reciprocal of the limit I just got, 1 over it. And so if this limit gave me e, then this limit over here is a special limit, and this will give me 1 over e, the reciprocal of what we just got. Now remember, 1 over e is not your answer. 1 over e tells you your answer. 1 over e is 2.7 ... 1 over e is less than 1. So what that tells me by the ratio test is that this series converges. Absolutely. And so let's run it again with one additional example. In this case, I'm going to use the root test. Even though I could use the ratio test, now that I know something about the nth root of n, it makes the root test a lot easier, right? All of these are great with the root test because they're going to cancel with the nth power. Here, I would be left with the nth root of n, but we just talked about what that limit was. And so now it makes it a little bit easier, instead of the ratio test, to take the root test here. Absolute value of my sequence. All the nth powers and nth roots cancel. The absolute value gets rid of the -1 to the n. And so what we should be left with is a single 2 in the numerator, a 5 in the denominator, and an nth root of n in the denominator. This is because roots split up over multiplication and division. So I can think of the nth root of the absolute value of this, which is 1 to the n, which just gives me 1. The nth root of 2 to the n just reduces to 2. The nth root of n, well, I don't know what that is right now. The nth root of 5 to the n cancels and gives me 5. Now, when I take this limit, though, we just talked about the limit of n to the n, the nth root of n, that goes to 1. And so now I have my answer is 2/5, 2 over 5 times 1. Most importantly, that number is less than 1. And so it tells me that this series converges absolutely. So these are some more involved examples because they require some additional information, but nonetheless, we can evaluate using the ratio and root test. And so here's just some additional practice, but they're nice examples, use some more information, and we can see how we can answer more complicated types of series with these tests. They're very nice tests to use. And so in the next video, what we're going to do is we're going to move forward, and we're going to stop with our testing of series, whether or not they converge or diverge, and explore another use of series or infinite sums. And the infinite sums we're going to look at are now going to involve functions. So instead of just adding numbers up, sequence terms, right, outputs of a sequence, we're now going to be adding up functions, so things involving x. And we'll start out finite, so we won't rush ourselves. We'll start out with finite sums of functions. We'll even be nicer, we'll do polynomials. And then we'll make that polynomial infinite. And that's where we're going to get an infinite polynomial, an infinite sum of monomial terms, and we're going to give a name to that. And so in the next couple sections, we're going to look at another application of series when it comes to functions.